Tonight we're going to continue in our notes on this unit, and tonight's topic is we're going to start off with just the idea of spontaneity, and it'll be both the topic of tonight's podcast as well as 8.6. And tonight we're going to be focusing on entropy. So in your notes, I think we're ready for Roman numeral 3, and we're just going to call Roman numeral 3 spontaneity of reactions. So spontaneity of reactions. Types of reactions is going to be the letter Roman numeral A. So types, and we basically have two types. We can have both spontaneous reactions and non-spontaneous reactions. And with spontaneous reactions, we might say that they proceed these reactions proceed without continual or continuous, but continual external influence and by external influence we really are just talking about energy. So energy is not necessarily needed externally to cause these reactions to occur. Alright, and conversely, a non-spontaneous reaction proceed with continual external influence, or you might say continual energy. We'll just abbreviate it a little bit. Alright, so that's the main difference between spontaneous and non-spontaneous reactions. All reactions will fall under one of these two types. So if we just jump into letter B, we're going to talk about factors that really affect spontaneity. Come on, pin. Oh, it's flashing, all kinds of craziness. Alright, so factors affecting spontaneity. And I think really with this, the first factor we're going to talk about is simply enthalpy. Alright, and what is enthalpy? It is essentially enthalpy, if I can spell it, enthalpy is heat at constant pressure. So enthalpy, it's delta H, or delta H of reaction. Alright, we've seen several ways to calculate delta H of reaction. Calorimetry is how we can measure it directly. If we have heats of formation, we can do it that way, or bond enthalpies. Alright, but if we have a negative delta H, okay, so negative H is so H is negative. That means that our reaction is exothermic. All right, and exothermic reactions are spontaneous. Okay, they are losing energy. They're going to a lower energy state, and they naturally want to do this. All right, spontaneously they want to do this. Why is continual external influence not needed? Because they're losing energy. The energy they're losing is really causing their continuous reaction. Okay? If enthalpy is positive, so delta H is positive, this is an endothermic reaction. Alright, or heat is going into our system, and this is requiring a continual external influence. Okay? So delta H's that are positive are non-spontaneous. Alright, so the heat of what we're really talking about tonight is going to be number 2. All right? And number 2 is known as entropy. And entropy is given the symbol S. All right? Most of them you're always going to see a delta in front of it. And entropy is simply disorder. If you like the word randomness, you can substitute randomness there. So disorder or randomness. And it has units of joules per Kelvin. All right? So it's temperature dependent. And the big thing is here, which you probably want to copy in your notes, write in your notes, highlight this, is that right there. Delta H is always measured in kilojoules. Delta G, which we're going to see in podcast 8.6, is always measured in kilojoules. But entropy always has the unit just joules. So it's always 1,000 different than our other 2 units. And here we go. We're going to kind of break this down into several subcomponents. The first being delta S is equal to, this is not going to be a surprise, S final minus S initial. Okay, no craziness there. That's pretty straightforward. If our delta S is positive, okay, so if S is increasing, that simply means we have more disorder, or randomness is increasing. And if randomness is increasing, or more disorder is occurring, this is spontaneous. All right. The best way to talk about this is you possibly, I know this happens at our house all the time, but we have to sometimes tell our kids they have to clean their rooms. All right. Why do rooms naturally get messy? Entropy. You can tell your parents this the next time they ask you. But Mom, it's the state of the universe. So stuff goes to disorder without the input of energy. Okay, and that's known as the second law of thermodynamics. Entropy increases in spontaneous processes. All right, second law of thermodynamics. If delta S is negative, that means that less disorder is occurring. Okay, so S is disorder, and if it's a negative sign, there's less disorder. And less disorder is always non-spontaneous. Okay? In order to clean your room, in order to make it less disorderly, you have to put energy into that room in order to make it less disordered. Okay? B. This gets into what we did in class today, in our, I think it was ChemQuest 54 possibly. But really, we want to find ways that we can predict the sign of delta S. Okay, so predicting delta S of reaction. Okay, predicting delta S of reaction. And we might say it is likely, and then we're just going to kind of list several times when it's likely. It is likely ... if the number of molecules increases in a reaction. And all this is saying is if we have more molecules increases in reaction, if we have more molecules on the product side than we have on the reactant side, that is likely a positive delta S. Okay, predicting delta S. It is likely, we should say over here, I'm sorry, it is likely positive if the number of molecules increase in a reaction. Another situation where it's likely positive is if the number of moles of gas increase in reaction. Right, so a couple times. And then a third instance where this is likely to take place is if we go from a solid to a liquid. Right, and if we think of a solid, it's fairly orderly. All of our molecules, or all of our atoms are trapped in place. And if it melts, so melting occurs, and we have a liquid, now those molecules are more free to move around, or more disorder has happened. The other time we can predict a positive delta S is if we're going from a liquid to a gas. Okay, same idea. Liquids are fairly ordered compared to a gas. Okay, and once we have a gas, it is the most disordered state. All right, and we are pretty close to being done tonight, which is awesome. All right, the last thing is calculating delta S. So calculating delta S. And pretty much we do this the exact same way. I know the last number on your ChemQuest today, I told you just to skip that in class because you will need your book, and we're again looking at Appendix A. But delta S of reaction is simply equal to the sum, all right, there's our sigma sign again, capital sigma, of the moles of products minus the sum of our moles of reactants. The equation is essentially identical to the equation we have for delta H in calculating that, and again, you're going to be using your appendix tonight. It is stoichiometrically dependent, so you will be multiplying the delta S values from the back of your book by however many moles you have in your balanced equation, and that is it. Have a great night.